Hello everyone, this is Alexandra Spyrou, and today I'm going to present to you a paper called NowPlaying, Continuous Low Power Music Recognition. This was authored by Google research team led by Gfeller, and it was published in 2017. To begin with, I would like to discuss with you the aim of this paper. So the aim was to create a low power music recognizer that can run entirely on a mobile device. So, being inspired by applications such as Shazam and SoundHound for music recognition, they wanted to create a similar service that could run entirely on a mobile device. In the existing methods, usually the user launches an application that captures several seconds of audio, and this application connects to a server for the recognition task. Unlike these methods, the main idea of NowPlaying is that all the user ideally would have to do is just glance at their phone and see which song is being played without unlocking the device. So they propose a novel architecture that doesn't need any connection to any server and is able to run entirely locally. It also runs on an airplane mode. And as Google states, it also helps preserve the data privacy. But the great thing about this application is that even though everything runs locally, it consumes less than 1% of the daily battery of the phone. Now I would like to discuss with you the model architecture. So as you can see from the figure, there are two basic components. First of all, there is a music detector that runs on a digital signal processing chip, and this is followed by a music recognizer that runs on an application processor. Now, the music recognizer it comprises also two modules, the fingerprinter and the fingerprint matcher. So briefly, the role of the first one, the music detector, is to be the gatekeeper of the music recognizer. And when it detects music, and only then, it wakes up the application processor and provides a buffer of audio. Now, the first component of the music recognizer, the fingerprinter, is responsible for encoding all songs in a database with unique hash codes. And the role of the second component, the fingerprint matcher, is to match a new query, a new music signal that comes as a query to an existing song in the database. A good question that you might have now is, what is fingerprinting? We can define fingerprinting as creating embeddings for the songs into a low-dimensional space. However, how can we treat songs? Songs cannot be processed in their raw format, so we can use short-time Fourier transform to transform them into spectrograms, and then when we extract the spectrograms, these can be treated as 2D images using traditional computer vision techniques. So ideally, we would like to embed its song into a unique vector in the space. And this projection should be able to preserve some song characteristics, some similarities in the space, just like we do with word embeddings in NLP, that we want to keep the semantic similarities in the space. So usually the method comprises two stages. The first stage is we want the image, the spectrogram, to be represented as a vector of features. Using traditional computer vision techniques, it could be traditional handcrafted descriptors such as hog or shift, or we could use a neural network to do that. The second stage is that the image representations need to be projected into the space and encoded as binary codes. This process is called hashing, and hashing can be performed both in supervised or unsupervised settings. The authors of this paper use a supervised method based on a neural network architecture that we will see on the next slide. So they use a single deep network, this fingerprinter, that consists of two stages, a convolutional stage and a divide and encode block, using triplet loss function, triplet loss objective function. This fingerprinter analyzes a few seconds of audio and emits a single fingerprint embedding at a rate of 1 per second. This part actually that I will discuss with you is not included in the paper, but in order to provide you with the full context, I'm going to simply explain to you how the network works. So they use a previously developed method developed by Lai et al. In 2015, which combines a triplet loss with the convolutional network and a divide and encode block. As you see on the figure on the left-hand side, this loss is based on triplets. So we have a query image or query song in our case, a similar song and a dissimilar song. Similar songs are considered only when the starting positions differ less than a few hundred milliseconds and they come from the same song. That's how they defined it in the paper. So triplet song spectrograms are the input of a stack of convolutional layers, and then they pass through an average pooling layer, and we get image representations as output. Then these need to be encoded, as we said, into binary vectors. The image representations are fed into a divide and encode module, and this module divides them into a number of vectors of equal length. Each of them is multiplied by a matrix and produces a scalar. The scalar goes through a sigmoid and is effectively mapped into a range 0 to 1. Then given the threshold that they have set, this is mapped to either a 0 or a 1. Finally, these values are concatenated to produce the final 3 binary codes. Now you might be wondering what's the use of the triplet loss. So as you can see from the right-hand side, the finger on the right-hand side, the triplet loss incentivizes the codes that correspond to the same song, the positive ones, to be at least margin m points closer than the negative codes. So essentially, it embeds the fingerprints from the same song by minimizing their distance to the query and enlarging the distance for all the others that belong to other songs. This is how embedding is learned into the space, and the value of m margin points is a hyperparameter that is set to 1 in this paper. Now let's move on to the second part of the music recognizer, which is the fingerprint matcher. So, as we discussed before, a song is not represented just as a sequence of fingerprint, but as a sequence of fingerprints, because the fingerprinter emits a fingerprint every second. So now, when we get a new query, a new song, we need to search that against sequences also of fingerprints that exist in the database. So for each of the fingerprints, they use an approximate nearest neighbor search, and they find the top k nearest fingerprints of that. As you can understand, each sequence now of fingerprints can be matched to multiple sequences in the database as we have k nearest neighbors. So the researchers selected the one that keeps the minimum average distance to each individual fingerprint. Of course, the most likely sequence might not be a good match, so as a result, there has to be a minimum probability for the sequences to match. However, they don't mention exactly the thresholds that they used. Last but not least, in order to avoid searching the whole database, they use a locative search sensitive hashing. This method, it's called also LSH, locality sensitive hashing. As you can see from the figure on the right-hand side, LSH partitions the space into distinct buckets using randomly generated hyperplanes. And when a new fingerprint is projected, a new query is projected into the space, we only limit the search within the partition it falls into. So they stated in the paper that when they search for a new query, only 2% of the database is actually searched, which is quite extraordinary. Now, what's the music detector? The music detector, as we said, is a gatekeeper that computes a probability of music playing in the background or not, and only then it wakes up the main application processor. This is a neural network and is a binary classifier that computes the probability of music playing in the background. It takes as input a stream of music in a time window and extracts its log mel feature vectors. And using those log mel feature vectors, it computes the probability of music playing or not. In total, it has 6 layers of convolution. However, in this figure, we show only the top 3 layers and 2 fully connected layers before the output. Every one of the stacks reduces the dimensionality of the input by a factor of 2. So every 2 in the power of 6 frames, that is every 640 milliseconds, it predicts an output if music is playing or not. The music detector is trained on a separate set. It's trained on a subset of audio set, but also some additional audio clips that they included noise into them, like office noise, speech, vehicles, etc., in order to increase the robustness of the method. And the data sets were all also annotated with information on whether music is present or not. In the final stage of the predictions, as we said, every 640 milliseconds we get a prediction, but this was not enough for, just a single prediction was not enough for the music detector to open the gate for the application processor. So the stream of predictions is averaged over a sliding window of a few seconds, and if we get at least 6 consecutive predictions with a probability greater than a specific threshold, then detection is registered and an audio buffer is sent to the fingerprinter. To keep memory and computational footprint low, they use low dimensionality for the whole network. Now let's move on to the evaluation part, where they test the performance on a real data set. First, they wanted to check the effect of the fingerprint dimensionality. So they found out that with fingerprints of lower dimensionality, we need less space on the device, and potentially we could have more songs in the database. They tested with 64 dimensions, 96 and 128 dimensions. Both 96 and 128 significantly outperformed the 64 dimensions. They had higher precision and recall. But yet the 128 dimensions don't significantly outperform the 96 dimension. Plus, they take 30% more space in the memory. So they selected 96 dimensions for the fingerprints. As we can see, they have achieved quite high precision and recalls. So the fingerprinter had a very good performance. And now they evaluate the performance of the music detector. When the recall, again, they tested against recall and precision metrics. They tested it against 12K short music regions, and what they found out was that when the recall was high, meaning that the detector detected a big percentage of the songs, the precision was getting low because a lot of false positives would come into. So a lot of false signals, let's say, for songs. So they made a trade-off here, and they accepted, they considered as an acceptable rate of false positive, 1 every 20 minutes. So this means that once in 20 minutes, we can have a bad signal, a signal of music, but it's not actually a song. But this was what they considered as acceptable, and they were able to achieve a recall of 75.5%. The other significant point was that the whole application consumed less than 1% of the daily battery of a Pixel 2 and a Pixel 2 XL phone, which was exactly what they wanted to achieve. And yet, however, they do not explicitly define the overall performance of the architecture, neither they mention anything about the performance of the sound recognition task. Now, let's move on to the limitations. As we can understand, the number of songs in the database is determined by the capacity of the mobile device. So it has a fixed capacity compared to what would have if it would connect to a server. So we have a limited number of songs, and potentially doesn't include any recently released songs. The second limitation is that using a hashing method in order to encode the fingerprints into binary codes has a risk of collisions. This is actually a really known risk of the hashing method, and it means that potentially it could lead to different songs being mapped into the same binary vector. However, this is not mentioned at all in the paper. We speculate that this was probably mitigated by using a high-dimensional vector, which achieved a higher accuracy. And the last point we have is that the song is represented as a sequence of fingerprints, and they did not mention any recurrent methods as an LSTM or a transformer to compress it into a single representation. So this means that when we get a new query, a new song segment, and needs to be searched, it needs to be broken down into individual fingerprints which need to be searched, and this can be more computationally expensive. Again, they don't make any mention about that or about future work, but we consider that this could be part of future work, as well as extending the database to even more songs. Overall, we think that this is a very interesting application, and indeed Google released that in 2017 on its Pixel phones. That was the end of the presentation. Thank you very much for your attention. Of course, if you have any questions, please leave them on the student forum. Thank you.